Our goal for this example is to develop a model for the two-span beam shown here. The beam is a W36 by 150 with two spans of 30 feet that is subjected to a uniformly distributed dead load of 800 pounds per linear foot and 12 kip live loads applied at the third points of each span. Ultimately, our objective is to examine the case where a variable load factor is applied to the dead load, as well as examine the potential of live loads that may or may not be present on the beam at any given time. As a first step, however, we will simply construct the model, apply the dead load and live loads, and then plot the shear force and bending moment diagrams for the two applied load cases, as well as ASCE 7 load combination number 2. Varying load factors and pattern live loads will be addressed in a subsequent demonstration. For this demonstration, we're going to be using the educational version, version 21, of the visual analysis modeling software. Okay, I'm going to start off with a brand new model, and one of the first things that I'm going to do is go to the project settings, and I'm going to modify the structure type. This is going to be a two-dimensional problem, so I'm going to select plane frame as the structure type for this model. The second thing I'm going to do is go in and set up the grid so that it's more appropriate for the extents of our model. We have a beam that's 60 feet long, so I'm going to set up a grid that has a little bit to the left and a little bit to the right of the ends of the beam, and in order to do that, what I'm going to do is set this up so that it has 34 divisions in the X direction, and then in the Y direction has 6 divisions. And those number of divisions, 34 divisions with a spacing of 2 feet, will give us a total of 68 feet in the X direction and a total of 12 feet in the Y direction. Now you can, let me tab out of that, you can see the grid modified here. Now that puts the origin of the model right in the center. However, I want the origin to be over here towards the left end, so I'm going to set the X location of that model at a value of 30 feet. Okay, now I can hold down on the center mouse wheel and pan that over, and that gives me a nice space to work with. The next step for us here is going to be to draw the model geometry. So in order to do that, I'm going to go to the Structure tab and then select the Draw Members tool. And what I'll do is just drag from left to right. And I'll click there at the origin and then drag to the right, watching the coordinates in the lower right hand corner of the screen until I get to a value of X equals 30. Then I release the mouse button, and that gives me that member. I'll do the same thing again, clicking on the node that was just created at X equals 30 feet and drag to the right until I get to X equals 60 feet. Alright, now as you can see, I have two members, but they are assigned the wrong cross section. I was probably using a W14 by 90 the last time that I worked in visual analysis, so let me hold down the shift key and drag a window to select those members. Then I'll go here to the project manager, and rather than selecting and modifying the 3 nodes, I'll modify the 2 members. Now if I go here to shape, I can click there and then navigate to the W36 by 150 and assign that as my cross section. Okay, next step for us is to define the support restraints. So there's going to be a pinned support here at the left end of the beam. So I'll click on that node and select displacement X and displacement Y as restrained and rotation Z as free. So dx and dy restrained or fixed, and then RZ is free. I'll go over here and select the other 2 nodes, and I'll just restrain dy for those 2. That makes those roller supports. So they're free to move in the X direction, they're free to rotate, but they are not free to move in the Y direction. Next, we're going to apply our loading to the model, and in this case we have a dead load that's a uniform load of 800 pounds per linear foot. And we have a live load that consists of point loads at the third points of each span, each with a magnitude of 12 kips. So the first step is to go here to the loading tab, and then I'm going to window to select both of the members, and I'm going to select the apply member load tool. and that opens up this dialog box. And for the dead load, I want a uniform load. I want it to be a force in the y direction, and I want a load with a magnitude of 800 pounds per linear foot, or 0.8 kips per foot. And I put a negative sign in there because I want the force to be in the negative y direction. Now, the next step then is to go ahead and apply the live load. So I'll go here to the service case and select L. It's grayed out because there currently aren't any loads assigned to the live load. I'll window those two members again, and then I'll apply the member load, and in this case I'll select evenly spaced point loads, force in the y direction, and the first load is offset by a distance of 10 feet, and then the spacing between the first and the second load is also 10 feet. In this case, I want point loads with a magnitude of 12 kips, and again I'll use a negative 12 to indicate that the loads act in the negative y direction. Now, as a last step, I'm going to go back to the dead load, and I'm going to edit that service case. So I select dead load D. I'll go here to edit load case on the loading tab or loading ribbon, and there's an option here to include self-weight. Now, the 800 pounds per linear foot that's stipulated in a problem includes the self-weight of the beam, but the way that this is set up now, visual analysis will add 150 pounds per linear foot to the 800 pounds per foot that we already added. So I'm going to select the no self-weight option, and that will eliminate the 150 pounds per linear foot self-weight of the rolled section. Okay, as a reminder, we have a lot of options here with respect to what we can display on our window. For example, right now we're displaying the section on each of the members. If we go here to Model Filter and go to Member Details, then we can hide that shape or that section if we want to. We can display the name if we want. In fact, while we're here, beam X1 and beam X2 aren't very descriptive names, so let me change those. I'll click on the first member there, and I'll call this span 1. And so that changes appropriately. I can come over here and do the same thing for the second member, call that span 2. We can go back to the model filter and display both the name and the shape, and visual analysis is smart enough to put the name above the member and the shape below the member. We could do the same thing with nodes if you'd like. We can display the name of the node. We can change those if you want to, but I don't think I'll take the time to do that at this point. Another thing we can do is look at the picture view of the member. And let me go ahead and pan around to a three-dimensional view here, and you can actually see the shape of the W36 by 150 and have some confidence that the member is actually defined with the web in the appropriate orientation. Okay, at this point we'll go ahead and run a preliminary analysis, and to do that I simply click on the Results tab in the main modeling window, and visual analysis conducts an analysis and gives us the deformed shape underneath one of the loadings. So the results case that we're looking at is live load right now, so that's the deformed shape of the beam under, I said live load, I meant dead load, forgive me. And we could also look at live load deflections if we wanted to, and it's automatically identified a few load cases that it thinks are appropriate. So we could take load combination number 2, where we have 1.2 times dead plus 1.6 times live, and look at the results for that. Let's go back to dead load for the moment. One thing we should check is the status. If we click on that drop down caret, we can go through here and just check to see if there are any warnings or errors, and I don't see anything out of the ordinary here, so it looks like the model executed correctly, and visual analysis at least thinks that we've done okay in our results. If we go down here to the bottom, the Find tool, you can see a bunch of tabs here with some results available to us. We have member displacements. If we click here, we have member forces detailed. And so if we look, we could sort by the member, span 1, and then the results offset, and that gives us the shear V sub y. and the bending moment M sub Z. So these are the bending moments that are in the beam. Up here we could display bending moments if you want to. A rather odd way of doing that here would be to, let's see, for the results we want to have results filter, and the result type that we want to show is, shoot, where's it at? Displacements, case summary. Member results, there it is, I'm sorry, moment M sub Z. So that gives us the bending moments superimposed on the deformed shape, and we can superimpose those on the undeformed shape if you want, and what that does is it gives us a contour of the bending moments. So the way that this is laid out is that dark blue represents a bending moment of 90 kip feet, and bright red represents a bending moment of 50 kip feet, red being positive, blue being negative. That's not very useful to us, and at least not in civil engineering for this type of a model. So we can go here to the member graph, and what we get are the displacements, the shear force, and the bending moment diagrams. But note that it only plotted this for span 1. If we go back to the results view, and if we drag a window over both members and then go to the member graph, then that gives us the shear force and bending moment diagram for both spans. And again, we can go back up here to the results case and look at the live load bending moment diagram, or look at the results of the load combinations that visual analysis thinks are appropriate for this particular analysis. Okay, as a next step, what I'll do is I'll display some numerical values in a report and then export them to Excel, where I can manipulate them as I see fit. So to do that, I'll go here to the report tab, and there's a lot of different information you can include in a report, and I'm not familiar with all of these details, but one that I use fairly often is a member force detailed report. So I grab that and drag it onto my report, and it gives me all of this information. Now we can manipulate that in a lot of different ways. We can go to the modify tab, and maybe I don't want all of the results case. For example, I'm not terribly interested in load combination number 1. So I can go in here and just select the ones that I'm interested in. I'll just select the dead load, the live load, and say load combination number 2. And that eliminates the other cases that aren't terribly interesting to me. I could also go in, and for the selected table, I can eliminate some of the results that aren't useful to me. For example, there's no weak axis moment, so no reason to have M sub Y. There's no weak axis shear, so there's no reason to have V sub Y. There's no reason to have an axial force F sub X, and there's no reason to have a torsion. I could also manipulate some of the other things. I can, for example, take the results case and drag it to the top. Let me try taking the member case and dragging it down there. There we go. Whoop, I went too far. So I want that to be there. I can't quite get it where I need it. There we go. And so now I have the result case as the first sort, and then I have the span, the member number, span 1, span 2, and then the offset here. So that will make it easier to manipulate the data later on. So there's some more things that we can do here. We can change the results offset. If you want data at the quarter points instead of the 10th points, then you can go in and type in 4. So that gives us, actually, yeah, so that's actually 10. Okay, so what I'll do at this point is copy the data using a tab delimited format, and then I'll go over to Excel and I'll paste the data in there, and you can see that data is ready to be manipulated any way we see fit. Finally, I'll take this data in Excel and I'll do a little manipulation here. I'll add a row to insert in between these different load case results. and then I can plot shear force and bending moment diagrams. So the offset that's shown here is relative to each of the two beams, so it resets when I go from span 1 to span 2, for example. So I'm going to go in and create a new column called absolute offset, and it's going to be in the units of feet. Let's copy that, put it there. So this is simply going to be equal to that for those cells, and then here I'm going to set that equal to that plus that, and then use dollar signs. So now I have absolute offsets for those. And let's see, now I can go in and plot those. Let's see, I can plot, oops, these two values here, go to insert and to a chart. I'll use a chart like that, and that gives us our shear force diagram. Okay, I can do the same thing and plot a bending moment diagram too if I want, like that. So I'll go ahead and go to insert, charts, and there is the bending moment diagram. Scroll down just a bit, bring that out, and that is the bending moment diagram for load combination number 2. Okay, there's a lot more you can do in Excel. For right now, I think that I'll go ahead and leave that as is. It's outputting a maximum moment at the underneath the 12 kip load of 187 kip feet, and here we're getting a negative moment of minus 300 kip feet. All right, well, that's I'll call that good.